Okay, it's me again. This is gonna be a video lecture that's really for fun. Is like serious and not serious at the same time. It is, I will be honest about it, to promote a hypothesis for what is actually the biggest mystery, I think, in cosmology or cosmogenesis, and that's the presence of dark matter, dark energy, and in the universe. We know it's there. Yeah, I will briefly pull up the article on Wikipedia. Wikipedia makes good articles on mainstream stuff. And dark matter energy, it was observed that there needs to be a lot more matter or energy, equivalent energy of matter and pure energy radiation in the universe than we see. Why? Because of the motion of galaxies or clusters of galaxies. So you can read about history. It's a mystery that is more than 100 years old. And it's kind of remarkable, I think, that popular writers like Penrose or Brian Greene or John Gribbins or whatever book you buy about quantum physics and cosmology is they talk about mysteries and strange things and quarks and all kinds of exotic particles. But dark matter, dark energy is a mystery that is absolutely left unexplained. And I said it's 95% up to 95% probably of a universe. So what could it be? So in that paper of mine, I came up with a very crazy hypothesis, which is actually a bit inspired by what I call Occam's razor principle. Occam's razor principle, he was a medieval monk who said, like, if you have a model, a mathematical model, it should correspond to, of course, what you want to explain, reality, but the model should be simple, should have, a model with somewhat less concepts and less degrees of freedom, or I would say, in your arsenal of symbols and operators, that's better. And Dirac sort of used that principle implicitly when he predicted the existence of the positron. He saw in his equation that, if I replace the negative electron charge by a positive one, it would work fine. So perhaps my equation shows that in theory, positrons, positively charged electrons can exist. And yeah, it was already actually before he wrote that there was some evidence that positrons would exist. Anderson admitted later that he was also inspired indeed by earlier experimental results that showed positrons might exist. So this is a very strange application of the razor principle, because I apply it actually to the electromagnetic force itself. For me, the electromagnetic force we can analyze in terms of an electric and a magnetic field vector that are perpendicular to each other. We can also analyze it in a much more advanced mathematical framework using 4 vectors and scalar and vector potentials. I don't do that here because the geometry sort of gets lost when you write these things down in terms of 4 vector algebra. But that's sort of what I would say radiation looks like. It's linearly polarized radiation. We can think it consists of photons. As I said, I think a photon, we can think of it being point-like, but it packs all of the energy in one cycle. So that would be the wavelength of a photon. But at any point on time, and that's the strange thing, a photon is at the place where it should be according to its equation of motion, and the electric and magnetic field vector are 0 everywhere else. The thing now is that the asymmetry that you have in that is that electric and magnetic field vector, they're perpendicular to each other, 90 degrees. but in a specific direction. Here I apply, all the conventions for geometry, the right-hand rule for defining an XYZ framework with the Z, the direction of motion of our photon. And I define, the imaginary unit as a rotation operator that folds or projects the x-axis onto the y-axis. That's a better definition than defining the imaginary unit as a rotation operator that is counterclockwise, because clockwise, counterclockwise, it depends in which direction you are looking. If we're looking in this direction, in the direction of the source, then we have a counterclockwise unit, or counterclockwise rotation. But if we look in the direction of propagation of the wave, which is given by the particular disposition of the electric and magnetic field vectors, then it's a clockwise direction. So I think I define the imaginary unit I as a rotation operator that folds the x-axis into the y-axis. So then, and that's not what I mean. Other papers I used more the counterclockwise or had, but that's sort of where the electromagnetic field or the magnetic field vector, and it can be written as vector B is plus the imaginary unit as an operation rotator times I, and then the magnitude is 1 over C, the magnitude of the magnetic field vector. So that's the asymmetry. And as you know, in physics we talk a lot about asymmetries and symmetries, charge parity and time symmetries. What I'm going to present here has nothing much to do with that. It's really, the idea was thinking about, when we look in the mirror, we see a virtual world. It doesn't exist. We look behind the mirror and that world isn't there. It's a trick of the mind. What we see really is the reflection of light that is reflected on us. So when we look in the mirror, the strange thing is, intuitively, because we look a lot in the mirror, maybe, we see a world that makes sense. We in the morning we shave ourselves, our girlfriend drops by, she appears behind us, we start talking, and the same thing happens in the mirror, and it looks like a world that is, possible. The people in the mirror, they talk to each other, they're a reflection of us, and so on. The things fall down, and also, when we start, and that's what I'm going to talk about here, and that's where things become difficult. We see a photon going from left to right, just like in the real world. Everything that happens there seems to be possible, but then we start thinking like, hey, if I want to really reach that guy in the other world, I give him my right hand. That's and he sticks out his left hand, and his heart is on is not on the left hand side; it's on the right hand side, and that's sort of the things that make you wonder, well, or can convince you the guy in the mirror isn't real. And here I reflect this image of a photon in the mirror, and I show immediately why that photon cannot be real, because if the reflection, the mirror image of this photon is, we have the electric field vector going up and down, oscillating linearly here, like this one, up and down, and but you will see the mirror, things that are near become far. So the magnetic field vector is it's in the wrong decision. We see the photon going from left to right here, but the magnetic field vector isn't okay. And if we start describing it, sort of using the conventions, oops, yeah, I should use razor principle. I can let that stand. We see a left-handed electron. If we call, the real electromagnetic force right-handed, applying all our right-hand rules for the mathematical right-hand rules and the physical right-hand rules for current and electromagnetic waves. Here we see a left-handed electromagnetic force, and that's why we know, well, this photon cannot be real. And I'm going to talk about that also. We can, in our real world, this photon can hit an electron, right? And it can interact, and so we're gonna see this photon here, which cannot exist, But in the mirror, we see, you know, a mirror image which looks quite normal, of the same electron or some other charge in the mirror, and that looks quite normal. And also there we will see that, oh, this photon, and that's what I'm going to be talking about. You know, a normal photon, a real photon, will when it hits a charge, it will give it a pushing momentum. And so here again, if we apply our rules, we should expect light. And let me explain that now. Let me go into detail here. I only have 2 slides. This is sort of an image I took from Wikipedia to explain, you know, if you have an incident electric field, you know, oscillating up and down. Oops, let me sort of round that photon. It's gonna cause the charge. We think of really the naked charge inside of an electron. The electron is inside an atomic or molecular orbital. It's gonna be absorbed, and in the absorption, the electron is gonna move. It's gonna also take, you know, absorb the oscillation of this electric field vector. It will go up and down. It will accelerate first up, and then it will accelerate down. So we will have a linear oscillation in space. And then here this thing is found, how does it look like? We can break it up in a radial component in the plane of the diagram, and then one which goes in and out of the plane of this diagram. That would be the tangential component, and from there, you know, we can do all kinds of things, derive a cross section and whatever. So that works for a linearly polarized photon. For a circularly polarized photon, we need to add the spin of the electric field as it goes through one wavelength. It will also go around its own axis of propagation and make one full well, like a wavelength, but more circumference of a circle. So then we just have to add a angular momentum, and the oscillation will not be linear, but will be yeah, the electron will sort of go round and round, you know, 2 linear oscillations that are perpendicular to each other make for an orbital oscillation. So the point with these pictures is, and that's kind of nice, is that we need to look at you know, the magnetic field vector as well. And so I can refer to something I picked up from Feynman's lectures, first volume 34.9 is, yeah, when you have a source of light, I said the electric force will cause the charge to go up and down, so it will give it some velocity, varying velocity. The magnetic field vector, this velocity of the charges, this is something you need to know. The charge here, the Q, is we assume an electron, so it's actually a negative quantity, minus the Coulomb charge, and here also minus the Coulomb charge, but that's a detail I'll go into later. Let's assume that you know, here we have that electric force, and I said it will determine the velocity of the charge. If the velocity is in direction, if it's positive charge of the electric field vector, or it's minus v if it's a negative charge, the magnetic field vector will be, as said, perpendicular to the electric field vector, but in a specific direction. And here I put it right. It's said it's a right-handed force, so it will be like this, and not the electric field vector. This one will not be there. That can't exist. And then applying the right-hand rule is that you know, the magnetic force will be the charge times the vector cross product of that velocity vector of the electron, VE, and the magnetic field vector. And indeed, the direction will be, if this is the crystal structure, this is one, and we have other charges. It will exert a pushing momentum on that charge. You may say, well, what if it's a positive charge? Well, the nice thing is indeed that the direction of this pushing momentum, it will always be pushing. It does not depend on the sign of the charge. Why not? Suppose we put a minus q. I said then the velocity vector will be in the opposite direction of the magnetic electric field vector. But we have then a minus v, and the minus q times the minus v, it gives the same direction of the magnetic field vector. So it would always be a pushing momentum. Light always has a pushing momentum, whether it be on negative or positive charges. And that's the thing here. When we look at this photon in the mirror, and it would hit an electron, negative or a positron. I said because the we would have, because of the orientation of the magnetic field vector, minus, let's sort of got erased, P minus the electric field vector divided by C. It would have a pulling momentum, or I don't know, because momentums are always not positive, but it would pull the charge out of the crystal structure or the material in which it happens to be. And so that's another thing that we say, like, okay, this mirror world cannot exist. The photon we see here doesn't make sense because it's not our force, and the electron that we see there in the mirror, it doesn't make sense because when that weird photon, dark photon would exist, then an ordinary electron, matter or antimatter, positron or electron, we would see it, would see that dark photon exerting a pulling momentum. So this is the thing I notice, when this explanation of mine, where I say maybe we have a dark force and we exploit that asymmetry. Let me clean up my sheet. It's not enough to assume that, oh well, we have a different force at work there, but for the rest, the photons in that world and the charges in that world are still the same as ours. No, that's not consistent, and it also wouldn't explain. Maybe some charge would arrive at us and it would behave the same way. No, the photons and the charges need to be you need to have a special quality, and so I also call them dark photons and dark charges. And so it's a whole, and that's the addendum I added in this paper on 2 days ago, the nature of dark particles. I explain very much in detail what I explained just now, and I add that it's a whole package, and a dark force and dark photon. You will say that this is a tautology, not an explanation at all. Said I assign, the nature of that dark quality I attach to not only the force but the photons and the charges is tautology. You say they don't interact because they're different. To that I would reply, and this is pretty serious actually. When you think about the quark hypothesis, which for me is still a hypothesis, I explained that elsewhere. I'm in a minority position with that, but I don't think quarks are real. Well, when you look at the qualities that are attached to them, it's pretty much the same. They it's stuff you don't find in the system of SI units. They get a color charge or a flavor up, down, strange, charm, top and bottom, and then there are new conservation laws, the conservation of strangeness and all these kind of things. So in terms of ontological or metaphysical or philosophical explanations of what quarks really are, I don't think my hypothesis is as crazy as it sounds. It sounds crazy, of course, but the nature of attaching this one and only quality to charges and photons in the dark matter energy world, this mirror world that we indeed don't interact with. These are the characteristics of the dark matter and energy that is out there. We cannot reach it. It's far away. We cannot see it. It doesn't radiate anything out. So it looks like yeah, sort of a mirror world. And that explanation is basically it. The one and only thing I want to add in my paper, and that's something I really invite you to think about, is I haven't done all that much research into broken symmetries, charge and parity symmetries. For me, I sort of wrote in my papers broken CP symmetries must be rooted in this asymmetry of the electromagnetic force. We have left-handed, right-handed particles, left spinning, right spinning. And that's the reason why certain, high energy particle reactions are probably not reversible. I'm thinking there may be something else now. I honestly think this is even crazier than the dark force hypothesis itself, but that maybe in some of these experiments we would see, dark charge or dark force operating. I hope so, because as I write in this paper, it's sort of, this hypothesis can only be confirmed if we would manage to find dark matter or dark energy, dark radiation in our world here on this planet, because the dark matter radiation, the large amounts, they're like hundreds of millions, 100 million light years away or more. A lot of it in the Coma cluster was the biggest one. There's also a lot of evidence for dark matter and dark energy in galaxies, in our own local group of galaxies, but we don't see any big masses of dark matter or dark energy in our Milky Way, and it's gonna be that's we're talking distances and which will never be reached by mankind, or if they can be reached, I'm talking about in 1,000 or 2,000 years from now, where we have I don't know, rockets with matter antimatter engines, and then we avoid but there's a lot of philosophical problems with that. Not real problems. Rockets that fly at any speed near light speed would be annihilated by any dust particle that they encounter. So no, we won't find it. So the only experimental thing, and it's done something maybe in 100 years, 200 years, but less than going out and visiting those areas of dark matter energy ourselves, is that we might discover or be able to produce a dark photon or a neutrino on the light particles. Dark charges, I don't think we'll have here, but maybe we can produce a sort of the anti-symmetric counterpart of our electromagnetic force. I don't know how, but that's a very remote possibility. But I talk about it here. So, but that's I'm gonna stop with this. I said it sounds really crazy. I'm at half an hour anyway. 20 minutes. That is fine. And look at that paper. It doesn't have a lot of reads, and I was happy about that. But I'm thinking, like, when I see all the nonsensical hypotheses, in my view, there's a whole list of them, and where is it here? Hypothesis. I don't know. Is it here? Yeah, light bosons, sort of special neutrinos, weak scale, other strangelet, superfluid, vacuum, three dynamical, primordial black holes. They might be modified gravities, particles that are formed, special gravitons or whatever. These are all fantastic theories, and I think they're so crazy that my simple ontological theory, I would say, is worth discussing at the occasion of a good Belgian beer in a bar with friends who would be interested in this matter. I'm going to talk about it with my brother in South Africa when I visit him next year, and then we'll have a good laugh about it. Yeah, I'm done, and And that's it. I wish you a very nice day and a fantastic